Hey there! Today we are designing a genetic algorithm and we are building a KNN classifier. So for this we are using the scikit-learn library and Python. So if you don't know what KNN classifier is, the k nearest neighbors, I I recommend you to watch another videos because I will not explain how the k nearest neighbors classifier works. I will just use the functions from the scikit-learn library. But if you don't know what a genetic algorithm is, I'll put in the card here my first video where I explain the theory behind the genetic algorithm and I build a version of it without using machine learning or anything. So the first step to design a GA is to understand what we need for the chromosome. So if you think about it, if we are trying to optimize the hyperparameters of a classifier, we have to check each parameters we can change and which options we have. So here we have the number of neighbors, weights, algorithm, leaf size, p, metric, metric params, and jobs. So as you can see, there are a lot of hyperparameters we can choose, but we are only using 3, and they will be the number of neighbors, the weights, and last the metric. So you can choose basically any amount of parameters you want, but you should know that anything you add to the GA will increase the search space, and a really large search space usually brings a lot of problems because we are only making about 100 tests, so 100 for a super large search space might be not much. So let's start with the number of neighbors. We have to choose which options are possible. So as the number of neighbors have to be integers above 0, I'm just choosing here. We are starting from 3 and the number can go all over 30. So we have 3 to 30 for the number of neighbors. The weight here can only have 2 options for this library, of course. So the first one, that is the default, is uniform, and the second is distance. So for the metrics here we have a bunch of options, which are those here, but we are not using all of them. I'm using about 6, I guess. So from all of those metrics, we have the metrics that people usually use more. So they are the Minkowski, Euclidean, Chebyshev, Jacquard, Cosine, and Manhattan. So those are the options we are given our genetic algorithm. So now we have our chromosome designed. So what all of those options represent? It represents that our chromosome will have this shape. First, an integer from 3 to 30, so 20. Then we must have a string, which can be uniform or distance. For this example, I'm using uniform. And last, we have a metric. So a metric is a string too, and should be one of those 6 options. I would choose Manhattan here. So our chromosome is any permutation of those options. Let's build it. So first we need some imports. The first one will be the class itself. If you haven't installed scikit-learn yet, you just need to open your prompt and type pip install scikit-learn this way and click enter. I have it already installed, so it shouldn't give me just the warning, the requirement already satisfied. So clear. The second thing we need is the accuracy score function. Then we need the train test split and load wine. So from scikit-learn we are only using those 3 functions in this class. This last one is our dataset. If you want to know more about this dataset, you can just search wine dataset. But basically we have 3 classes, which are wine 1, wine 2 and wine 3, and we have a bunch of examples. So we are training our KNN to predict if a wine is from class 1, class 2 or class 3. This dataset is really interesting because it's already on the scikit-learn library, so your pip install will already download it for you. And we have the random imports too we use on the last. So I will not explain everything because in the other video I have gone line per line. So the individual will be the exactly same, so I'm not going through functions. The first thing you will notice that is really different is the initialize, is the constructor here. So as you can see, we have xtrain, xtest, ytrain and ytest. So if you don't know what those are, I really hope you have gone through other videos to understand what KNNs are and classifiers are. So I'm not really explaining for what we made this separation. But now when we call our class, we first have to load our dataset on this data frame variable. Then we have to split this dataset into train and test. So we have xtrain, xtest, ytrain and ytest. So moving on, we call the train test split function. And now, as we already have our data frame here, we have to pass the data, which are the features of the data frame, and the targets. The targets here are just 1, 2 or 3, which are the wine classes, and we have to pass the test size and the random state. You don't have to put the random state here, but it's cool if you want to reproduce the genetic algorithm multiple times. So the random value don't change, it's the same every time. So we are splitting 30% for test and the rest for train. Now when we call our class, we pass the train and test data and we initialize it. But forget this for now. So back to the constructor. We have passed the train and test values here. We create the attributes. So this variable here I'm just using to later build a graph that I will show, so don't bother this right now. Those three are the same from the previous video: the max generation, population size, and the percentage of the mutation. This best individual here is the same too. And last we have our chromosome shape. So this is the most different part of the constructor, which will give all of our options. As you remember, the range varies from 3 to 30 on our index 0 for the number of neighbors. Then on the index 1 we have uniform and distance, which represents the weights, and all of this is our second index, which represents the metric. The first method is exactly the same as the previous video, because we are just using the choice on the chromosome shape. So the first choice returns a number from 3 to 30. The second choice returns uniform or distance, and the third returns one of those 6 strings and returns the individual class. Now the generate population method, it's exactly the same too. We just are appending random generated individuals to the population. Now we have the fitness function. This function is really the most different one. So we pass the individual. We are trying to calculate the fitness. But the first thing you should know is that the fitness here on this genetic algorithm, as we are trying to get as many classes right when we are predicting, so we are using accuracy as fitness. So if a chromosome predict more classes right than the other, its fitness will be higher. Okay, so the index 0 of the chromosome represents the number of neighbors, which I'm using n here. Then the index 1 represents the weight we are using, and the index 2 represents the metric. So now we call the class and we are making a object of this class using number of neighbors equals to the index 0 of the chromosome. The weights are the index 1 of the chromosome, and the metric is the index 2 of the chromosome. Then we fit the classifier on the X train and Y train we have splitted here. So now our model is trying to predict using the features of the test split. So here we get an array of 1, 2, 3, 1, 2, 3, 1, 1, 1, 2, the predictions of those features. And here we get the accuracy using the function accuracy score. We pass as parameters the true values of the classes and the predictions we made. So it basically will calculate how many of the total of the tests the model got right. And now, as I said before, the fitness is the same as the accuracy score, so fitness, accuracy. To end the function, we repeat those lines of code from the previous video, so we just are keeping the best fitness here, so we can print on the end of the process and we return the fitness we have calculated here, which is the accuracy. Then we have the population fitness method, the selection method, which continues to be the same. The crossover, which again is literally the same. The mutation, again. And last, we have the initialize method, which is the same again. I almost forgot the writes methods, so the write generation and write best. As I said before, I made a little change here on this code. I added this section where I calculate the mean accuracy of each population, and I append on this self.means, which I said I'll explain later. So basically, let's say we are on the first generation, then each individual of this population fitness will be added together, and then we divide by the length of the population, which ends up on the mean of the population. The file name here, which will be KNN_GA, and the rest I think it's the same. It's the same here. Okay, the part that we change is that after each generation is written on the file, we add this accuracy mean here. So we above here we summed each of the 10 accuracies and we divided by 10, which is the population length, and then we print it right after. And the last method is the write best, and this is the same. We just write best individual and we grab the best individual dot to string, and we print all the generation means in the form of an array. It will help me further build the graph. So all the classes are finished and we have already loaded our wine dataset. So now I will run it and show you the results I got, as well as some graphs, so you better understand the genetic algorithm and how it helps searching basically anything you can put on a chromosome. Finally, here are the results. So on the generation 0, or the first one, the mean accuracy we got was 0.72 or 72%, but the highest one was 79%. On the second generation, or generation 1, the best we got was 83%, and the accuracy mean increased by 6 points. By 5 points. So in the third, we continued on the 83%, but our mean is increasing, as you can see. 77, 79, 80. Here a little drop, but it's pretty normal, some drops like this. 82.7, 82.9, 83.7, a little drop, and we finished on 83.7%. And our best individual was the chromosome with 28 as the number of neighbors. And a really interesting thing here is that distance as the weight and Manhattan as the metric really dominated the later generations. Probably this Chebyshev and Cosin here came from mutations. Yes, came from mutations, as the generation 7 was all Manhattan, and out of nowhere we got Chebyshev and Cosin here. Really interesting, and some of them are the same. So our best individual, 85.18%, and the first time it appears was on the generation 3. And to finish the results, we have the generation means. So now I'm going to put on the screen some graphs I have generated. So this is the first one. We have, as the title says, GA accuracies through generations. So basically on the first generation we got something between 72 and 74%, the lowest one as well. Then on the second generation we had something between 76 and 78, and it goes on. As you can see, it's clear that the tendency of the accuracies is to increase. This is the main point of the genetic algorithm. So I made a little linear regression here, so you can see truly the tendency. This dotted red line indicates that the tendency is really to increase. Of course, if you made 100 generations, it probably won't keep increasing. It probably will remain in a straight line after some generations, as this last graph here shows. I made 30 generations, so I basically ran the program again, but changed the max number of generations to 30. And as you can see, after the 8th generation, the mean of the accuracies just remained almost as a straight line, and this green line represents the linear regression of the first 10 generations.